Let's go ahead. So thank you so much, Nikhil, for agreeing to speak to us. So Nikhil has done a lot of amazing work on discrete optimization, and I'm especially familiar with all of your great works on discrepancy theory, which is amazing stuff, making that finally computational. But today, Nikhil is going to tell us about the optimal gaps between quantum and classical query complexity. And I think I'm just going to let you jump right in.
Okay, thanks, Rasmus. Thanks for the invitation and the introduction. Yeah, it's a pleasure to be here, even though online, but still. Yeah, so I'll talk about some joint recent work with my postdoc, Makran Sinha at CWI. It's about optimal gaps between quantum and classical query complexity. And again, if these words don't make sense, that's fine. I'll explain everything. And one thing about this talk will be, you don't need to know anything about quantum for this, and not even much about query complexity. Like whatever you need, I'll explain. Because ultimately, all these, the question we'll see will just boil down to understanding like certain Gaussian distributions in high dimension. So yeah, so ultimately it'll just be a question about probability once we like unmask everything. So yeah, so let's begin. Okay, so one of the main goals in quantum computing or quantum complexity is to understand, how powerful quantum computers are over, let's say, classical computers. Do they buy us anything or maybe not? So again, there are various models to ask this question. Like one can look at the formal Turing machine model in the quantum setting and so on, but not much is known there because in general we don't know how to prove lower bounds for anything. But one setting which has seen a lot of progress is a setting called query complexity, where one can actually prove unconditional lower bounds. And as I'll show you in a couple of slides later, almost all quantum algorithms we know, like even the complicated ones like factoring and so on, do fit in this query complexity model. So this model still captures a lot of algorithms and all that we know, at least so far. So, okay, so what is this model? So let's look at the query complexity model in the classical setting first. So here we are given some function that we are interested in. And let's say it's a function on n bits, like -1, 1 to n. And let's say it's a Boolean function to 0, 1. And we want to evaluate it on some input x, right? But this input x is not given to us. And the way we access this input is like our query algorithm. Each time it will give a query to some black box, which will say, what's bit number I, and then we get back xi. Then maybe based on the value of this xi, it might ask another bit, and then it gets the value, input value on that bit, and so on. And at some point, we announce the value of f of x on that input. Right? And the query complexity is like, to evaluate a particular fx, how many bits do I need to query? Right? So, or in other words, we can think of this as a decision tree, like this whole algorithm, querying algorithm, right? You first query a certain bit, and depending on the outcome, maybe you query another bit and so on, and until when you reach a leaf, you output the answer 0 or 1, right? So for a function f, the decision tree complexity is like, what's the lowest depth decision tree that computes this answer, right? So I hope the model is clear. It's probably many of you have seen it. Okay, and one can also, so this is like a deterministic model, what I just described, each time you get answer. You can also ask a randomized query complexity, which is just, you can view that as your algorithm is like a probability distribution over some decision trees. And here your goal is like for every input x, you should be able to answer it correctly, let's say with some better than half probability, right? So let's say 2/3, right? So for every input x, your query algorithm should compute the right answer with some non-trivial probability, and then you are interested in the lowest depth of these decision trees. Okay. Right. So when you first see this model, it might look a bit artificial. I mean, what can you really do in this setting? Like you would expect like for most functions, you probably need to query most of the bits to get anything meaningful. But let me give you some sense for why this is a very general model. So in particular, like you can view this as a meta problem which models itself a lot of things. So let me tell you what I mean by this. So right, so let's say you have some function f on n input bits, so x1 through xn. Now you can think of this x1 through xn as actually encoding the truth table of some function on log n bits, right? So a function on log n bits is completely specified by like 2 to the log n values, so n values. So you can think of this x1 encoding like what is g on a certain input, then x2 encoding what's g on a certain input, and then querying a certain xi means you're asking the evaluation of g on a certain input, right? And your function f now could be sort of a meta function which says like this. So when you evaluate, you're kind of figuring out the value of this little function g, and maybe you're interested in whether this little function g is a dictator or not, right? And your big function kind of decides whether this little function is a dictator. So you already see like you can encode a lot of things, and for example, dictatorship testing is a widely used subroutine, in TCP and all, and we can do like very clever algorithms with constant number of bits and so on. So anyway, so the point is, yeah, you can encode a lot in this model. Okay, good. Okay, and now what is quantum query complexity? So here, sort of the difference is that you have a quantum algorithm, and now when it makes a query to this black box, the input can actually come out. It can like query the input in superposition. So what does this really mean? So maybe just 1 minute of like very, very basic quantum stuff, which we won't even need, but maybe it's good to know. So you can think of, if you have log n qubits, it sort of encodes a quantum state on 2 to the log n or n. You can sort of encode the entire state of this quantum system as an n-dimensional vector with like complex entries. Okay, and the way a quantum algorithm works is, it has some quantum state which is encoded in this n-dimensional vector, and it can basically apply unitary transformations to this. Right? It's like applying a gate, and it can do queries on the input. And what a query does, so again here, so think of a query as, right, so I is from 1 through n, so these bits sort of encode the n, like the dimensions of this n-dimensional vector, and you can sort of read all these bits at once, even in principle. But somehow, okay, even though you can read all these n bits in one query, these bits are not really usable because they're kind of encoded in this quantum state, right? And one interesting thing about quantum systems is, even though this quantum state encodes a lot of information, but when you try it, the only way you can extract information out of this is sort of try to make a measurement. But then the moment you do a measurement, sort of everything collapses, and you only get sort of 1 bit of information. So even though like this information is all encoded in the quantum state, it's not really accessible in a direct sense, right? So again, you don't need to understand this, but just the difference here in quantum algorithms is that, yeah, you can read this input in sort of a superposition, you can read many bits at once, and that's really one of the magics of quantum computing. So one way to think of a quantum algorithm could be the following: like you start in some initial state where all your probability mass or the amplitude is on this the zeroth dimension, and then you sort of apply some unitary, and then you make a query, so it gets some superposition of inputs. Then you maybe apply another unitary matrix, then another query, and so on. And then you're interested in how many queries you made. So let me give a couple of examples to make this a bit more concrete. Okay, so one of the most basic questions in quantum computing is like this Grover search, which was a surprising result. So here the setting is the following: you have like an n-bit string, let's say of 0 ones, and you want to find if any bit is 1, right? So it's really or function, right? And classically, you would need n queries to kind of figure this out, right? You have to see every location to figure out if there is 1 somewhere or not. But in the quantum world, you can do this with about square root n queries, and this is also tight. And this is this famous Grover search, which probably everybody has heard about. Okay, so yeah, so here the improvement is like from n to square root n. And as we all know, like sometimes this improvement can be much more dramatic. So we all know about factoring, we can do much faster. But before factoring, there was a more basic problem called Simon's problem, which it's kind of artificial, but it's kind of a useful one to understand. It's about finding patterns in your data. So what is Simon's problem? So here the input is from n numbers to n numbers, right? So it's not from 0, 1, but we'll worry about that later, right? So it's from n to n, and you are given the following promise: either this function is a permutation, so all of fx are distinct, so it maps each number to a distinct number, or there is some very specific pattern here. So there is some binary string s, and every f of x XOR s is f of x, right? So then it will be like it's a 2-to-1 function, right? So every two values map to the same place in some very specific way. So for every x, and yeah, so these two evaluations are same for every x, right? And in the Simon's problem, you are supposed to figure out this hidden string s. Okay. So again, the way you can classically solve this problem is by sort of randomly evaluating randomly asking queries, and then you hope to like hit a collision in about root n steps, right, by the birthday paradox. But turns out, yeah, in quantum world, you can just do this with log square n queries, so you get an exponential improvement. And these kinds of things are the key to factoring. And more generally, there is something called period finding, which you can also do in log square n queries. Okay. Yeah, maybe other things. So, right. So again, all these things, so the output here, strictly speaking, is not binary, right? It's not 0, 1, but one can do encoding tricks. That's why you lose these extra log n's here and get this. Similarly, another sort of famous problem is element distinctness, where you have n entries and they're all mapped again to some output range, say m, and you want to figure out whether they're all distinct or there is a collision. And classically, you need about n queries, and quantum you can do better, right? Okay. Yeah, so somehow you can really exploit this superposition in non-trivial ways. And yeah, so and the whole game in this quantum versus classical query complexity is to understand, what's the extra power that quantum is buying you over classical. Okay. So before we go further, we need to understand one important distinction between functions, which plays an important role. So a function can be total or partial. So by a total function, we mean, it's defined on every possible like 2 to the n inputs. It has either value, let's say 0 or 1. A partial function is one where we only care about a subset of inputs, right, where the value is 0, 1. And for other inputs, I mean, either the value doesn't exist or maybe we don't care. Right? So partial function looks something like this. And it turns out that this makes a big difference. So just to get a feeling for what I'm saying, so let's first look at just deterministic versus randomized query complexity. Right? So forget all about quantum. And suppose I have a partial function. So it's only, I only care about certain inputs. So it's 0 if all the bits are 0. So on the all 0 string, it's 0. And it evaluates to 1 if it has exactly half ones and half minus ones. Okay, or half zeros and half ones, I guess. Yeah, so like if it's completely balanced, the input string, then it's outputting a 1. And if it's all 0, it's outputting a 0. Now, again, deterministically, you'll need about n queries, the worst case, to figure out whether it's an all 0 string or half. But as you see, like randomized, you can test this, just with constant number of queries, right? Just evaluate a few random positions. And if you are in this case, you will see both like zeros and ones or plus ones and minus one. And so here, like the gap for this partial function can be really large, order 1 versus n. But an interesting fact is actually if you had a total function, the gap between randomized and deterministic complexity can never be more than quadratic. Right. So somehow allowing partial functions really can make a big difference. Okay. Good. So let me just, so it's kind of a bit mysterious maybe if you see this for the first time. So let me demystify this a bit. And And again, it's a whole lot of work on this, and it's a sort of very beautiful area. So in general, if we look at these three complexities, the query complexity of a function, the randomized complexity, and the deterministic complexity, now clearly this is the order of them for any function. But turns out if you have total functions, all these quantities are polynomially related. And sort of one reason is, so in fact, all these quantities are related to some very basic parameters of this function f, such as approximate degree. Like if you write f as a polynomial, what's the degree that you need? Something that's called certificate complexity, something that's also called another parameter called the block sensitivity of this function. And probably you heard of this recent breakthrough that happened last year, where this very basic property called sensitivity of a function, right? If you just flip, how many times it flips in the neighborhood. So even that is closely related, like polynomially related to all these parameters, right? So somehow you can characterize total functions very nicely in all these quantum randomized deterministic settings, right? And there is like a huge amount of work and even ongoing work to sort of improve these exponents in these quantum versus randomized versus deterministic, like what's the exponent. So for instance, if we just look at one particular dimension which we could study and which will be relevant for us later on, is if you ask classical randomized queries, right? So if you have a total function which you can compute by some number of quantum queries, like how many classical queries do you need? So there was a classic result of Beals, Bierman, Cleve, Mosca, de Wolf, which showed that you don't need more than 6th power. So if you can do something in like k queries or k quantum queries, you can do this in k to the 6 randomized classical queries. And this was actually, I think it's an upcoming stock paper where this has been brought down to 4. And then people have also been trying to push it from the lower bound side, like separations between randomized classical queries and quantum queries for total functions. And the best bound prior to our work was 8/3 here. So upper bound is 4. And there are functions where there is a separation of 8/3. Okay, so this is sort of just some story about total functions. So let's move on. So what about partial functions? And that's where the interesting thing happens, and you get these exponential gaps between classical and quantum complexity. So so I already mentioned this Simon's example, this problem of finding this hidden string S, where quantum queries were log square n versus root n. Okay, and there has been a long line of work sort of improving or like making this separation further and further. And at one point, Bierman, Fortnau, Newman, and Rode conjectured, can we get even a maximal separation of like 1 versus n? Right, so notice you can always solve everything in n queries, like you never need more than n queries. So this is really the worst possible separation. Like quantum, you just need 1, and classically you need almost n queries. Okay, maybe I should say, like when I write n, of course I'm ignoring constants, like so n should really be thought as omega n and so on. So I wouldn't bother. So I'll just so when I would say 1, there is no 1 is really 1, but when I say n to the 1/4, it's omega n to the 1/4. So so this question kind of motivated this field, and the best known gaps until a few years ago was 1 versus root n by Aronson and Ambinas. Okay, so you can ask, could this gap 1 versus root n be pushed further? But then Aronson and Ambinas in the same paper showed that no, actually this is the tight answer for one query quantum algorithms. In particular, they showed a more general result that any k/2, let's say with ceilings, quantum query algorithm can be simulated with n to the 1 minus 1 over k classical queries. Right? So in particular, if k is 2, so then this is one quantum query, and 1 minus 1 over k is a half. So you get the 1 versus root n. So so this is like a positive result. You can always simulate a quantum algorithm with like these many number of classical queries. So you can't improve this gap further. And and this gap function was actually achieved by a function called Fourrelation, which we'll study a lot in the next few minutes. And this Fourrelation stands for this word Fourier correlation, and this will be clear why it's called like this. Okay, good. Okay, so more importantly, also in that paper, they conjectured another function, which they call k-Forrelation, and we'll also see this later in the talk. And they conjectured that this k-Forrelation actually gets this k over 2 versus n to the 1 minus 1 over k gap tightly. Like, so this gap would exactly match what they could achieve algorithmically, right, in the simulation. Yeah, so they conjectured not only is this gap tight, but they gave us very specific function for which this separation should be possible, the correlation function, k-Forrelation function, and they couldn't, yeah, and this was conjectured. Okay, so our result, which I'll talk about in this talk, is that we can indeed show that for this function, you get this optimal separation as they conjectured. And again, I'm ignoring some lower order terms and some error parameters and so on, but yeah, right. So basically, you get this optimum separation between quantum and classical. And as we'll see sort of later in the talk, things were stuck at root n somehow, even for like k equal to 3. So k equal to 2 corresponds to this classical Fourrelation, which they prove 1 versus root n bound. But even for k equal to 3, like it wasn't clear how to push this. And there had been some recent works trying to go in a slightly different direction. So last year there was a very nice paper by Avishai et al, which gave a different function called row relation. So yeah, this is not a typo. It's actually R instead of F here. And again, I haven't defined what this Fourrelation function is, but yeah, so it sort of replaces a certain component in that by a certain random orthogonal matrix. That's why F becomes R. And so it gives like it's like a probabilistic method kind of a proof. So it gives a non-explicit function. And he could push this gap all the way to like n to the 2/3. And very recently, so in this upcoming talk, Sherstov, Storozenko, and Wu could take this row relation function and push the gap all the way to this conjectured bound. So again, I'll try to give some highlight of what they do, like some taste of this. But as we'll see, like this approach is very different from what we do, and in fact, what their approach sort of provably cannot work for this k-Forrelation function, which is this explicit function. But again, all these things will make sense. I'm just giving sort of overview. Okay, and one small thing. So right, so we proved this sort of bound for this k-Forrelation, and using sort of other previous work. One corollary of this result is that it also improves this bound for the total functions that I was telling about earlier. So previously this bound was like this 8 over 3 here of randomized query complexity versus quantum queries. And this can directly, like if you can just plug this result into, there is a certain framework for sort of transferring bounds for partial functions to lower bounds for total functions called the cheat sheet framework. And using that, you get this cubic, this strengthening. So yeah, so we are kind of getting closer to understanding this gap. So the upper bound is like a 4 here and the lower bound is 3. So still some ways to go. Okay. Okay, so I think this is a good time for sort of questions. This was just roughly the overview of what is query complexity and what the problem was and what are our results. So are there any questions at this point? Okay, if not, let's continue. So here is the rough outline of the talk, rest of the talk. So I'll explain what this Fourrelation and k-Forrelation problems are. And then we'll see like all this, we can just forget about all of this and just reduce this down to a problem of understanding two different distributions, right? So it'll just become like a problem about probability. And then I want to explain you the square root and lower bound for Fourrelation. Like even though this was known already in the work of Ambayanis and Aronson in like 2014, So actually their proof was quite complicated. It's like a 60-page paper. But there is a very nice sort of, yeah, and we'll actually do this full proof using sort of stochastic calculus techniques, which Raz and Tal developed a couple of years ago, sort of in a slightly different context of separating pH with BQP. And the stochastic calculus approach wasn't explicit in their work, but it was made explicit in this note by Yingyu Wu, who's a student at CMU, or was a student at CMU. Okay, but what I'll use this is to explain you a very nice technique called Gaussian interpolation, which, as we'll see, it also has like a lot of amazing other applications. So it's a very cool technique, which actually I didn't know earlier, and I think it should have many applications. So I'll spend some time on explaining what this Gaussian interpolation is and give a couple of examples. And then I'll sort of briefly talk about the k-Forrelation problem and why things were stuck at root n and why these two previous works of Abhishek Tal and Shersov needed to invent this row relation problem. And what do we do roughly to get around this? But I'll be a bit sketchy here because somehow, yeah, things get quickly very technical. So I'll try to give a flavor, but yeah, we'll see. Okay, so that's the rough outline. So let's get started. Good. So here is the definition of the Fourier problem. Okay, so it's a function defined on 2n bits. So we'll think of it as x1 and x2. x1 is the first block of n bits. x2 is the second block of n bits. And we'll work with -1, 1 instead of 0, 1, just so that it'll be easier. Okay, so I'll write it like this. And yeah, and it's a partial function which is defined as follows. So yeah, so I'll take the Hadamard n by n Hadamard matrix. So again, just to maybe remind you, Hadamard, it's this standard or the Fourier matrix where each entry is either +1 over root n or -1 over root n, and all the rows and columns are orthogonal to each other. So it's an orthonormal system, rows and columns. So in particular, it's a unitary matrix. It preserves the L2 norms. Right. So you take the Hadamard matrix, normalized so that each entry is 1 over root n, and you do the following. So you take these x2 vector, right, multiply it with the Hadamard, and they take the inner product with x1, the first n bits, right, and then you, right, and now this function outputs a 0 if, okay, so maybe, yeah, so this number, the inner product of x1 and h of x2, it's always between like -n and n, because x1 and x2 are vectors with entries +1 and -1, so they have like L2 norm root n. So h of x2 also has L2 norm root n because Hadamard preserves the L2 norm, right? So this quantity is between -n and n. So divided by n is between -1 and 1. So right. So this function kind of, yeah. So it outputs a 0 if this quantity is small, or in other words, x1 and h of x2 are almost orthogonal, and if they are sort of highly correlated. Right, so let's say bigger than some constant 0.1, which is much larger than this 0.01, then it outputs a 1. Right? So it's again a partial function because it's not defined, like we don't care what happens sort of between these two ranges. Right? It's sort of also like a promise problem. So it's 0 if it's very small in a product, if it's very large, it's 1. Okay, and our job is to distinguish between these two cases. Okay, so right, so given an input x1, x2, I need to figure out whether this inner product is large or small by doing these queries, right? That's the problem. Okay, now turns out this problem can be solved by just one quantum query, and again we don't need to understand how it's done. Like, it's actually a very simple way. Like if we know quantum algorithms, it can be very easily set up to just do it with one query. Right. Okay, and as we'll see, like, yeah, so and classically it will take root n queries. That's what we'll show. Okay, so let's define some notation. So I'll call this problem, or like Aronson and Ambanes call this problem Fourier, or the twofold Fourier, and maybe right. So again, going back, the reason is, so h of x2 you can think of as computing the Fourier transform of this string x2, and then it's finding the correlation with the first string of n bits x1. So it's kind of Fourier correlation. So that's fine. Correlation, and yeah, and if we expand this out, it's this bilinear form, and maybe it'll be useful to think of it as sort of a graph where you have these n bits here and n bits there, and you have this n by n Hadamard matrix, and you look at all possible pairs and kind of sum them up. Okay, so that's the correlation function, and we need to distinguish between these two cases. Okay. Right. So the only thing you need to sort of remember, and I'll keep reminding this many times, this definition of the correlation function. Good. Okay. So and then there is the k-fold correlation, which then they conjectured to give this k over 2 versus n to the 1 minus 1 over k gap. And then we'll revisit this later on, but I just want to show you. So now this is a bit more messy function. So here you have k blocks of n bits. So the input is like minus 1, 1 to kn. And again, you want to distinguish whether this input, this correlation function is very small or very big. And the correlation function kind of generalizes like this. Yeah, so maybe it's easier to look at this picture. So then you have these, so this is for k equal to 3. You have these 3 blocks of n bits. And now you look at all possible, paths like this. So sort of n, yeah, so whatever, like from every pair to every pair here, and then every pair to every pair there. And you multiply x1 i1 times x2 i2 times x3 i3 times the edge weight, which is this Hadamard weight, right? And you sum them up. So it's just some kind of like tensor, and we'll see later why this sort of comes up naturally. Okay. So again, for now, you just need to know what is correlation. Good. So yeah, so I just defined what is correlation and k-correlation. But now let me get to, how do we sort of reduce this problem of getting query complexity to just a problem about distributions. Okay. So I mentioned that this correlation 2 problem can be solved with one query. And we want to show a lower bound that any randomized classical algorithm takes a lot of queries. So let's go back and see how does one show randomized lower bounds. So there is only sort of one way, and probably many of you have seen this. It's Yau's minimax lemma. So typically, if you want to prove a randomized lower bound on worst case input, you try to come up with some distribution. You sort of reduce this to showing a deterministic lower bound, but over distributions over input. Right? And usually showing deterministic lower bound is much easier. So this is a very powerful technique. So let me make this more concrete if you haven't seen this. So our goal always while proving randomized lower bound is somehow to come up with two distributions, D0 and D1, where D0 is kind of mostly distributed on these 0 inputs. So, maybe it has most of the mass here and maybe some of this here and so on. And D1 will be mostly distributed on 1 inputs. Okay. And now, if you could come up with these two distributions, which are sort of very far apart in terms of, how the correlation function evaluates on these things. But if you could show that any deterministic decision tree with sort of low depth or depth D cannot distinguish between, so if I give you some input from D0 or some input from D1 and I ask, where is it coming from? So it can always guess randomly and say D1 and, it can always get it half with, correct with probability half, but to get anything non-trivial probability of success, if you can show that you need a large depth decision tree, then you have proved a randomized lower bound. Okay, so yeah, this is standard technique. So let's see what we have accomplished. So really what this does, if you could figure out how to design these distributions D0 and D1, right? Once you have those distributions, it's really about showing, I have these two distributions that any deterministic decision tree cannot distinguish between them with few queries. Right? So ultimately, this allows you to boil down this question about sort of separating two distributions. Okay, good. So for this correlation problem, let's see what are these two distributions. They're actually very, very natural. So the first distribution will be just uniform on 2n bits, right? So each bit is random plus 1 minus 1, right? Yeah, on each of these 2n bits, n and n. And it's easy to see that, since it's completely random, like h of y is again basically a random vector and x is a random vector. So in fact, their inner product will be very close to like 1 over root n, right? Because they were between -1 and 1, but if they are sort of orthogonal, then the absolute value of the inner product will be very small. So in particular, if I pick just random bits, yeah, they're very close to 0 most of the time. Okay, so this will be our distribution D0, like mostly distributed on 0 outputs. And okay, now let's see for what about distribution D1, which is mostly distributed on output value ones, or like inputs where the output is 1. So let's do a thought experiment. So suppose, okay, so yeah, I'm writing xy here, but yeah, x, you can think of it this as x1 and x2. So suppose if I choose x1 to be h times x2, right? So my correlation function was this inner product of x1 times h of x2, right? And if x1 is chosen as h times x2, right, this numerator here is just the squared norm of this, which is just a squared norm of x2, which is n. So the correlation value is 1, right? So in particular, at least, yeah, if x1 was h times x2, this correlation value will be very large as opposed to here, what it was. Now, one slight trouble is that x1 may not be a +1 minus 1 vector. Right? It's not a Boolean vector anymore if we take h times x2. So x2 is a +1 minus 1 vector, but h, yeah. But still, right, we expect each coordinate of, right. So in fact, yeah, if you do h times x2, each coordinate will look like a Gaussian with variance 1, right? Because you're summing lots of +1 minus 1 vectors with like 1 over root n coefficient. Right. So again, sort of you can convince yourself that, okay, it may not be exactly +1 minus 1, but it's sort of the squared expectation is exactly 1 of any coordinate. So there is some technicality one can do, which I don't want to sort of get into. One can pretend that we can sort of pretend that this is +1 minus 1. So, okay, maybe let me say a couple of words. So in the Avishai et al. Paper, so they do h times x2, scale it down a little bit so that it is between -1 and +1, and then you can do a randomized rounding, for instance. And the point is it morally still retains the flavor, because in expectation it's still sort of this value h of x2. So one can play such tricks and sort of get back to -1 world, but we'll sort of not worry about this. So for simplicity, we'll just think of this distribution D1 in the following way. So this x2, instead of a +1 minus 1 vector, we'll actually pick a random Gaussian with variance 1. Right. So the x2 part is a random normal 0, 1 vector in each coordinate, and x1 will be h times g. Right, so h Hadamard times this g. Okay. Right. So notice, yeah. So x1, x2, now the coordinates become mildly correlated, right? Because the covariance, right? So yeah, g is completely random vector, but x1 is sort of correlated with x2. And if I look at any two coordinates I and j, the correlation is about 1 over root n. Right. So the point is, even though, okay, so what have we accomplished? So if you choose these, if your input distribution is this, g and hg, the correlation value is large, right? It's sort of 1. Right. So yeah, so the correlation value is large, and because you have coupled these vectors slightly, but it's a very weak sort of coupling in some sense. And because it's so weak, somehow that's what will let us do root n queries. So let's make this a bit more precise. Good. So our goal now, because once we have given these distributions, the goal is the following. So we have distribution which is completely uniform over these 2n bits. And again, we'll think of this as independent Gaussian on these 2n bits. And this distribution D1 is, so this is a completely random Gaussian, and this is h times g. Right? So notice if, if I just look at h times g itself, this is also distributed like a normal 0, 1 to the n, because all the columns of h are orthogonal, right? So h times g will also sort of have covariance the identity matrix. But if you look at this joint 2n dimensional vector, it will have this covariance. So like this block of G will have covariance identity, the block of HG will have covariance identity, and the cross covariance will be this H, obviously. Okay. So yeah, so we have these two very simple distributions, the independent 2n dimensional Gaussian and one Gaussian given with this covariance matrix. And we want to show that any decision tree that's trying to distinguish a sample from one of these distributions will require a lot of depth. That's our whole goal. So what we have accomplished so far, we can forget about correlation and everything. It's just this problem about distinguishing inputs from these two distributions using a decision tree. Good. So any questions maybe at this point? Because yeah, this is the problem sort of we have abstracted out, and this is what we'll work with. Okay, so if not, yeah. Right. So let's see, so we want to prove this, right? This is our goal, that you need a big depth decision tree to distinguish. Now, what is a decision tree, right? So this is, we can view like a decision tree is kind of, okay, we can view it like this, but we can also view it as some function, right? That this decision tree is computing on these sort of n or 2n bits. And if it has depth d, it's like a degree d polynomial, right? So we want to show that sort of you need a high degree polynomial, but something seems a bit funny. So, okay, so first thing we can try to show is that any distribution, any sort of polynomial that tries to distinguish between these two distributions should have high degree. But this is not true, right? Because in fact, there is a degree 2 polynomial which can distinguish between these two distributions. Like the Fourier polynomial, it was just a bilinear form of degree 2, and it actually distinguishes between D0 and D1. Okay, so we need to use something more about this decision tree. And some of the punchline is that decision trees of depth d, even though they are degree d polynomials, they are sort of limited in the sense that they cannot encode dense polynomials. So what do we mean by this? So I'll make this more precise in the next slide. So a nice result of Avishai et al. From last year is that if you look at the, okay, so so look at your polynomial that this decision tree is computing, right? This function, write it as a polynomial. And if you look at the degree L monomials and you sum up the weight of their coefficients, that can't be too large. It's like d to the L over 2 roughly. So let's ignore this log n. Okay, and we'll sort of see in the next slide what this really means. Yeah, so W1 LF is just the like level L weight, L1 weight of these coefficients. Okay, so let's actually make these things a bit precise, and let me do a bit of Fourier analysis, like very, very basics, which we'll need. So again, if you are given any Boolean function on -1 to the n, 1 to the n to some real value, we can write it in the Fourier basis, like these, in the monomial basis. Right? And these f hat s are just the correlation of fx and the this parity function. Right, and we also know, these form orthogonal bases. Okay, so some basic facts that we'll use. So if you take expectation of this fx over all, x uniformly -1, 1, then all these things average out to 0 except the average empty Fourier coefficient, right? And that's f at 0, standard fact. Similarly, if I'm looking at the derivative of this function, let's say derivative with respect to xi, then if I take the derivative with respect to xi here, only the Fourier coefficient corresponding to set S, which is element I, will survive, will become constant, and everything else will either have this some x sitting on it or 0. So if I take expectation, you just get the Fourier coefficient of I and so on, right? So if I have some multiple derivative and I take average of all of this, it's just going to be f at ij and so on. Okay. So yeah, just very basic Fourier analysis. And also, yeah, maybe fact that, right, so Parseval, we know, so, right, just because these are all orthonormal, if you, so expected squared value of f is same as sum of squares of Fourier coefficients. So in particular, if your function f was bounded between -1 and 1, which will always be the case for us. So we'll assume that f is this, always represents some decision tree that whose depth we are trying to lower bound, right? So then we know the sums of Fourier coefficients are not bounded by 1, sums of squares, right? And yeah, and this is the notation I'm using for the L1 norm of the Fourier coefficients with weight L for these with S equal to L, right? So in general, we can always bound this number, the W1L can never be more than like n square root of n choose L, right? Because there are n choose L monomials like this, sets of size L, and we know that squared sum is at most 1 by Parseval. So just by Cauchy-Schwarz, you'll get that the L1 norm cannot exceed this, right? So what Tal is showing is a much more refined bound compared to this naive bound, which is like d roughly d to the L over 2 as opposed to roughly n to the L over 2, right? So if f is coming from a decision tree, so in this sense, the functions coming from a decision tree are a bit limited of depth d. Good. Okay, so what have we achieved so far? So right, so we want to show, again, our goal is that if you have a function given by a depth d decision tree, and we have these two distributions d0 and d1, that, yeah, if you can show that, so if you take sample from this distribution d1, which I'll call p, and another sample from this distribution d0, the uniform distribution, then this f cannot, if this value is small, right, the expectation, that means f cannot distinguish between these two distributions. So yeah, so the Keylemma that we'll show using stochastic calculus is that this difference is at most like the level 2 weight of this function f divided by root n, right? And by Thal's bound, that the level 2 weight is like at most d log n, right? This is this lemma from the previous slide, right? So if L is 2, this is at most d log n, right? So in particular, what, yeah, if we prove this, that if we prove this, this will imply that the sort of the distinguishing that you get by f on these two distributions is bounded by this number. So if your d was like smaller than root n over log n, this gap is little of 1. So you cannot distinguish between these two things, right? So our goal will be to show exactly this, that if you have any function f, right, and if you evaluate it on x coming from this distribution or x coming from this distribution, the gap is bounded by this quantity. Okay. All right. So how do you do this? Yeah. So again, P, recall, was GHG and U was completely independent Gaussian, and we want to understand this gap. Right. So here is a very powerful technique that's precisely tailored to answer this question. And yeah, so it's called Gaussian Interpolation, and it says the following. So suppose you have two Gaussians, like n-dimensional Gaussians, G and G prime, with some covariance matrix U and U prime. Okay. And suppose f is some n-variate function. And of moderate growth means it's not growing like e to the x square. So yeah, so as long as it's not like growing faster than e to the x square, we have the following precise formula. It says that if I evaluate my function on a random Gaussian from the first distribution minus expectation when I evaluate f on a Gaussian from this distribution, it's exactly this. So let's parse what's going on. So, right. So we sum up over all I and j. Okay, U and U prime were the covariance matrices. So I look at the difference of the entries. And then I look at the ijth partial derivative of f. Okay, and I evaluated at some point called gt. Okay. Okay, so what is going on here? So, right, so we have two distributions, g prime and g, coming from covariance matrices u prime and u. Right, and I want to understand kind of the gap of evaluating f on this in expectation minus evaluating f on this. So in Gaussian interpolation, what you try to do is you have these two covariance matrices. You sort of imagine you start with one Gaussian coming from here, and you slowly interpolate it to this Gaussian by changing the covariance matrix, like in the obvious way by taking a convex combination. So again, this is PSD, so it's a valid covariance matrix, right? And yeah, so that's, so GT is like a Gaussian which is coming from this covariance matrix. Okay, so the point is, yeah, so we'll see what this really buys us. Maybe it looks a bit scary and mysterious, but the point is there is a very precise formula for understanding the behavior of f for two different Gaussian distributions. And somehow the point is, if you want to understand f on some complicated distribution g, you can start from some simple distribution g prime and sort of interpolate using this formula and see what happens, right? And often, if you can control this quantity, you can get great bounds. So Talleyrand actually calls this method the smart path method, and there are lots of powerful applications. So let's see just the two-line proof of what we were trying to prove for the correlation function. Right. So yeah, so we have these two distributions. One is this completely independent Gaussian, the other is this correlated Gaussian. Okay, and the covariance matrix for this U is just identity. For P, it was this. And we wanted to understand the value of F on these two different distributions. Right, we wanted to show this. This is where we had reduced the Fourier problem. Okay, so if you just apply the Gaussian interpolation formula, it's exactly tailored for what we wanted, right? So this difference is exactly, so I'm just writing the Gaussian interpolation formula. So now let's see what this does. So this is the final covariance minus the initial covariance. So yeah, so the final covariance for us is this, the initial covariance was this. So the difference for any entry ij is either 0 or 1 over plus minus 1 over root n, right? Because the only way these two covariances matrices differ is by these entries h, which have 1 over root n entries. Good. Okay. Yeah. So the point is, yeah, all these numbers are just either 0 or plus minus 1 over root n. Good. So this is what's going to give the root n here. And now let's look at this number. Right. So it is just some second order partial derivative of f. And we kind of saw that partial derivatives of a function, if we average over them, it's basically corresponds to the second ijth Fourier coefficient, right? Now, yeah, I'm cheating a bit here because, yeah, if you are averaging over the completely uniform distribution, this would be exact equality. But one can do some tricks, like even though we are now averaging over this intermediate distribution pt when we interpolate, you can still do some standard tricks and sort of show it's roughly the same. But yeah, but let's believe this for now. So once we have this, right? Yeah, you're just summing up over all ij, so you'll get the L2 weight, L1 weight at level 2 divided by root n, which was this. This is exactly what we wanted to prove. Okay, so Gaussian interpolation, just like in one line, gives us this amazing thing, right? How f behaves on two different distributions. So let me actually describe a couple more examples. Maybe I'll skip the second interest of time. So so you can prove all kinds of things, and actually Talleyrand's book on spin glasses has lots of very nice examples. So again, one which I particularly like is this very famous result about Gaussian concentration of Lipschitz functions. So let's say if you have some function which is one Lipschitz, so fx minus fy is like at most the L2 distance between X and Y. Now, sort of classic result and a very useful result is that this is very tightly concentrated, right? Like if you evaluate it at a random Gaussian, its variance, like it decays like a standard Gaussian with variance 1. As opposed to like if you did Azuma Hofding or something, it would only give you a much weaker tail with like variance n instead of variance 1. Right. So, oops, sorry. Yeah, so one can prove this in a very simple way using, so again, there are many proofs of this standard fact, and somehow all the other proofs that I've seen are always very mysterious or magical. But here is a very clean way of proving this using Gaussian interpolation. So, right. So we want to show that, okay, Fg has some exponentially decaying tail. So we can look at some exponential moment of this thing, right, and prove it's like e to the lambda square, which would imply it's order 1 sub-Gaussian. So that if you're, so proving tail bounds is the same as proving moment bounds, right? And by using Jensen, we can sort of replace this by independent copy of this, right? So if we show that this guy is bounded by e to the lambda square, we are done, right? So again, this kind of becomes like a question of understanding two different G and G prime. So what one can do is interpolate from the setting where this G and G prime are the same, in which case this is just exponential of 0, which is 1, so very simple, to like this setting where G and G prime are independent, right? So yeah, so maybe I'll skip the calculation, but the point is, yeah, like if you just apply interpolation and use the Gaussian interpolation formula, you get that this quantity, again, it's like a one-line computation, is basically, it satisfies this differential equation that phi prime t is at most lambda square phi t, which means like phi should grow like e to the lambda square. Right. So again, yeah, so I went a bit fast over this, but the point is, right, so you want to understand some complicated object. You start with some very basic object where this guy is always 0, so it's trivial, and then you just interpolate it, and you have very explicit formula, so you can just find this. Another nice example of this is, which I'll skip now in the interest of time, is this dramatic proof of this Gaussian correlation conjecture due to Royan, which was open for many years. But yeah, but it's a very nice, simple but with some tedious computation, but conceptually quite simple using this Gaussian interpolation. But let me skip that.
I think, Nikhil, if you want to go a minute over to say it, you should absolutely feel free to. But you decide.
Okay, so I can do two. I'm seeing, yeah, I can either talk about this or the k-Forrelation a bit. Maybe
I get you decide, but it would also be good to hear about the k-Forrelation, I guess, given the title. Okay. So either one.
Okay, maybe in the question and answers we can talk about the Royan stuff because it's very cute. That's what I want to show. And yeah, I'll just say a couple of words about this k-Forrelation. Good. Yeah, I'll try to wrap it up in 5 minutes. Okay. So just, yes. So basically, right. So see where we are. We finished this proof of Fourier order 2 Fourier, right? Just using Gaussian interpolation. At the end of the day, it became just like a one-line computation. Right. So now if you look at k-Forrelation, so then just to remind you, it was this messy formula. Okay, I don't know, somehow something got deleted here, but yeah, it should be like many levels here. This is for 2. So let's just look at k equal to 3. Okay. Yeah. So it turns out, okay, so again, we want to show that any decision tree takes a lot of sort of depth to distinguish them. So we'll do the standard thing, come up with 2 distributions, D0 and D1, sort of one 0 input and 1 input, where this correlation function takes different value, and show that any classical decision tree cannot distinguish them. So it turns out, again, the distribution D0 is just, you take, right, so I'm looking at k equal to 3, so now there are 3 blocks of n bits each, so I'll just take the uniform distribution. But the D1 distribution, so earlier when we had only one block, it was or like these two blocks, it was of the type G comma HG, but now it becomes something more painful. So the right distribution is you pick a Gaussian here, pick another Gaussian here, and on this intermediate block, you compute H times this Gaussian, H times this Gaussian, and then take the sort of coordinate-wise product, right? So like the ith entry of this vector is the ith entry of this vector times the ith entry of this vector. Okay. So the reason is if you plug this distribution, again, what will happen in this formula is that you'll get a big number. So again, I'll skip the computation, but basically you get this, and these both are like unit vectors. So if the values look like this Fourier function is large. Right? So these are two natural distributions where Fourier function is large. So again, if you wanted to show that no classical algorithm or decision tree can distinguish them unless it has a lot of depth, all we need to do is take this distribution D1, which I'm calling P, right, and show that any small depth decision tree given by F minus when X was coming from this uniform distribution on this thing. Okay, sorry, this is a typo. This should just be X, yeah. Right, that they cannot. Okay, no, okay, yeah. Right. So this is the Fourier function, right? So yeah, so if we can, like similarly as in the Fourier 2 case, we can show that this gap is small. But the point is, if we now try to apply Gaussian interpolation, so the first coordinates are Gaussian, this is Gaussian, but this guy, it's not a Gaussian anymore. Like these entries are product of two Gaussians. So it's not immediately clear how to apply Gaussian interpolation. Okay, so what these other work, yeah, so this is where all sort of previous approaches were stuck, right? Like if you try to do for k equal to 3, somehow this nice technique that worked earlier with this Gaussian interpolation somehow seems to get stuck. So these two previous works which tried to get around this using this row relation function, so they applied a bit more hands-on approach. So let me show you what I mean. So again, we want to sort of bound this gap, right, when X comes from distribution 1 or distribution 0. Okay, so we can write this as just by expanding the Fourier formula as this, because if X is from uniform distribution, this is just the empty Fourier coefficient. So this is just this. Okay. Now, if we can get a handle on this quantity, so let's separate that out. Right. So if I sum up over all S of weight L, it's this weight times this. Right. Now I have a good handle on these Fourier level weight at level L. Right. So yeah, this is by the Fourier bound on decision trees. So if we could control this quantity, then we can show that this number was small, right? But turns out like this Hadamard matrix is bad for that reason. This number can actually be pretty large for Hadamard, because Hadamard can have a lot of large blocks with all +1 entries. So this norm can become very large. So the idea of Tal was, okay, so let's replace this Hadamard by sort of a random orthogonal matrix, right? And random orthogonal matrix has this nice property that you don't have sort of big blocks of all ones or all -1s, or so you can sort of bound this number, and then he could use it to push it all the way to n to the 2/3, this gap, for this row relation function, because this bottleneck didn't bother him. Okay, but this bound was still a bottleneck, and there was this recent result, which is in this upcoming talk, where Cherstov et al. Can improve also this bound on the Fourier level weight from d to the L over 2 to sort of a more refined bound of d choose L square root. And the point is somehow when L, yeah, so even though they look similar, like d choose L is morally like d to the L, so this looks like d to the L over 2. But when L gets large, sort of this bound is much more loose compared to this bound. Okay. So somehow by refining this first part of a tighter Fourier bound for decision trees and using this random orthogonal matrix, he could push it all the way to n to this gap, like n to the 1 - 1 over k for row relation function. Right. But for us, yeah, since we need really this Hadamard matrix for the correlation function, somehow, yeah, these ideas don't help because you're still stuck with this bottleneck of having, it's a very specific matrix with these large block of ones, which messes up these estimates. Okay, so maybe just one line on what we do. So basically, we have a way to extend this Gaussian integration approach, and for correlation 3 function, we can prove the following bound, like between these two distributions, the gap of f is like the Fourier weight of degree 3 monomials over n, and thus the Fourier weight of degree 6 monomials over n square. So it's a bit more complicated than what we had for the 2-level correlation, right? And now because we have such a nice formula, yeah, you can just show that even if you use the weak bounds of Avishai et al. For these Fourier weights, it still allows us to get d to like n to the 2/3, which is the right answer for k equal to 3. And more generally, we can have a formula here for correlation k, which only requires Fourier weights of up to level k square. So that's still d to the L over 2 is a very good estimate, and we get this bound. So let me just say one word about the trick that we need. So we need a second Gaussian tool. So the first tool was Gaussian Interpolation, which worked for 2. But here we need another tool. So let me just mention this identity because it's kind of very cute and might be useful in other contexts. So again, suppose you have some n-dimensional Gaussian and another Gaussian function, Gaussian random variable u, and let's say u and g are jointly Gaussian. So u is a scalar and g is a Gaussian vector, but they are still jointly Gaussian. And suppose you were interested in some complicated function of these Gaussian vector times this u, which might be correlated in funny ways with this g1 through gn. Turns out there is an exact formula for this. Right. So maybe the thing to notice here is that, okay, there was this product here which was annoying, product times u. So here the product has disappeared and you have got a partial derivative, and this is just some constant, right? It's just the correlation between this u and gi. You sum up over all that, right? So it's kind of a very precise formula which allows you to trade off like a product which you may not like for some reason with like a derivative. And again, sort of, yeah, I don't have the time why these products come up, but sort of this was, okay, maybe it's one word, right? So because, in this correlation 3 function, you had this intermediate block which looked like product of two Gaussians. When you apply Gaussian interpolation, you get sort of these spurious terms, which, when you take the derivative of this, like one free hanging g, but then you can use this Gaussian integration by parts to kind of eat that up and get another derivative. So somehow, yeah, you can sort of clean up the thing. And yeah, so for k equal to 3, one can still apply this in a relatively clean way and get this bound. And for k greater than 3, things get a bit more messy because, to clean up like one thing here, you get n things here. And so one needs some complicated argument, sort of counting argument to argue that this process converges at some point. So anyway, so yeah, I'm a bit quick here because I underestimated the time. But the point is, yeah, this is a very nice identity. It's like exact identity, and it could be useful in other places. Okay, so let me maybe just conclude. So we saw this optimal separation between quantum and classical query complexity, and these questions essentially boil down to distinguishing distributions. So it's just all about probability. And one of the things we did was use kind of Gaussian techniques to answer questions about Boolean functions. And recently this idea has been quite popular, and there have been several other papers which are doing this, like Ronan Naldan and Ramon Van Handel and so on, where you kind of prove long-standing questions about Boolean functions using sort of Gaussian techniques. And so I think, yeah, this is a very useful direction, particularly if you work with Gaussians. It allows you to take these derivatives, which you can't really do in sort of the Boolean case. So, you can pass to the continuous world. So Gaussian interpolation and this Gaussian integration by parts are both examples of this sort of using continuity to argue about things. And so I hope, yeah, these ideas will have more applications in general. So let me stop at that, and thanks for your attention.
Thank you, Nikhil. And let's have maybe a moment for people to ask questions.
Okay.
So I just want to mention to everybody, A, that you can ask questions in the chat. We can also put you on audio if you want to ask a longer question. And B, after we're done, we're going to go to this lounge mode for a little bit. Then you can say hello to Nikhil if you want. Okay, we have Johannes.
Oh, I see. There were a couple of questions in the chat.
Yeah, we got those answered though along the way, I think. But okay. Johannes was
right.
So do you see this question from Johannes? In quantum query complexity, do you restrict measurements to n-1 dimensional projections?
Wait, where is this? I don't see that. Oh, in questions. Okay, I'm looking at chat. Okay.
Yeah.
Do you? Yeah. So actually, I don't understand. What do you mean by this thing? So measurements are still. You just like get to one state in the end, right? Or with the correct amplitude.
So when you I think Ming, can you put Johannes on stage with us? Sorry. Let's see if this works. Maybe I can also do it. Oh.
Great. Thanks. I think you can hear me, right?
Yes.
Yeah. So the thing that I'm a bit confused about is, I mean, in quantum computation, as far as I understand, it's always possible to push the measurements all the way to the back, right?
Yeah.
So in this sense, if you so by what I usually understand by measurement, I mean, in every quantum computation, you only need one measurement, right?
Yeah, that's right.
So but this is also somehow not what you mean, I think, because then one measurement can give you more than one bit of information, right? It can give you something like n bits of information.
Okay.
And this is something. I mean, I think I could still kind of get the idea, but this is something that puzzles me, or that I can't completely square.
Okay, yeah. So one point I hand waved, about this. So let's say your output function that you're interested in is only like value 0 or 1, let's say, right?
Yes.
So then you can just think, 0 I'm encoding by sort of one state 0, 0, 0, and 1 by like another quantum state 1, 1, 1. And I can set up my algorithm so that it, like, when you measure, it goes in one of these states with the right probability. But often in these, let's say, like in Grover's, you actually want to find the index of the string, not just like detect if it's all zeros but maybe. So then, then you would set up your output in such a way that you actually get the answer, right? So you won't measure so that you just default to just two states, 0 or 1, but maybe when you do the measurement, it will like point you to the index of the place where you have a 1.
Right? Yes, but then how do you actually ever get a quantum query complexity that is larger than 1? If every quantum computation you can reduce to just have one measurement, and then I mean every quantum query complexity should be 1.
Okay. No, so let's look at, let's say, Grover search, right?
Yes.
So so you read all your input. but then like the way Grover search will work, right? So it will sort of, okay, so you read your input at some quantum state, and you maybe, but then you measure it again, and that measurement kind of allows you to move again, and then you measure again, like you interact
okay,
with this.
I see, yeah. Yes.
Yeah, I don't know, right? Like every time, yeah, you interact with this input string, you kind of rotate, and after root n rotations, you kind of increase your amplitude to this place where there is 1.
Yes.
So that's like the query. Because indeed, like the first time you read it, it's not really usable. I mean, you have this, exactly. So it's like reinforcing itself every time once you read the input. Right, like this location that has a 1.
Yeah. No, that makes sense. Thank you.
Yeah, because we didn't talk about what quantum algorithms do, so it's a bit vague, but yeah.
Yeah. It's a little bit. I think it's just a little bit long ago since I last looked into quantum algorithms. Right. So
yeah.
Let's see. I think we could still take another question if anybody has one. Otherwise, let's thank Nikhil again. This is super interesting, Nikhil. I'm going to ask you more questions. I guess it's not offline these days, but in the lounge. Okay. Yeah.
Yeah. Thanks a lot.
Yeah.
Perhaps just one very quick remark to Rasmus. I think there was a technical problem at the beginning of the talk. So for some reason, perhaps this was planned, but I wasn't aware of it. It required a new registration before you can actually log into the talk. So this was why I was kind of 2 minutes late, and there were also a lot of other people being a bit late.
Yes, okay. We'll work on that. Thank you.
Yeah.
Okay.
It was no problem, just that you know why all the people were late.
Yeah, okay. Very good. Thank you. Okay, Ming, maybe you can wrap up the session for us.